Alright, so particles A and B collide on a frictionless surface. A is twice the mass of B. So in the back of your head, just remember that you're going to have to remember that you'll need to times it by 2 in terms of relative momentum. Alright, so for starters, let's actually get the measurements going here. So this one here is actually 76 millimeters, and that's spread over 2 divisions. So the distance between the frames is actually 38 millimeters. Okay. Then I'll go over to this one here. So that one is 51. So it's going to be 51 divided by the 2 divisions, which actually gives me 25.5 millimeters. Now this one I'm going to use 3 divisions here, 1, 2, 3, just so I can be a bit more precise. So this actually comes out to 41 millimeters. So 41 divided by 3 is equal to 13.7 millimeters per division. But to change that to a relative momentum, it's twice. So I'll times that by 2, which gives me 27.4. And I'll do the same thing over here. I'll use 4 divisions, so that comes out to 34 millimeters. So 34 millimeters divided by the 1, 2, 3 divisions, which gives me a separation of 11.3. Remember, don't forget to times it by 2 because of the mass, and then that actually comes out to 22.6 millimeters. Now we have to get the angles, and this is not a very nice setup. Okay, so I'm just going to draw some lines in order to work the geoliner. Now, because it doesn't meet perfectly, I'm going to draw the best right angle I can through here. Now I've already pre-measured these, so they need to intersect this line here, and I need to draw another parallel line through here. Okay, so the angles that I measure are going to be all right there. Okay, so getting the first angle here, position the cross point to here, make sure the line levels up, and you actually get an angle of 97 degrees. Now I've already done this angle in here, and that's actually equal to 6 degrees. This angle in here is 70 degrees, which is nice and convenient, and this angle in here is actually 12 degrees. Alright, just a reminder, on this side is the initial, and on this side is actually the final. Okay, because they come together, collide, and move away. Alright, so let's do the vector diagram. So I'm going to put in my reference point here. Now, because these distances are quite small, if you wanted to get a more accurate answer, I'd just double the size, and that way your diagram will have a bit more precision. Alright, so I'm going to put this bit here as my starting point. So let's actually start off with initial A vector. So that actually drops below the line at 12 degrees. (10, 11, 12). And that actually has a length of 27 millimeters, so 5, 7. So that one's actually A initial. Now we're going to do B. I'm going to draw in my parallel line so I can actually, so just a very light pen line there, just the weight of the pencil, and that needs to go off at a 70 degree angle. or 110. Just lining it up carefully with the point there. And that needs to have a length of 25.5 millimeters. And that's B initial. Okay, so now we need to do the final momentum. So there's A, and that's at an angle of 97 degrees. So again, go back to my starting point, which is there. So 7 degrees, and that needs to have a length of 22.6. So 10, 20, 1, 2. As you can tell, this diagram's not going to be too precise, but then now I need to do my parallel line. So here's my starting line. See how I'm just lining it up with the text. That should make it fairly parallel. And I need to do a 6-degree drop. So using my G-liner here, 6 degrees there, and that needs to have a length of 38 millimeters. So if I line it up here, line it up there, there's 38, and that is very close. So yes, I would actually say that momentum is conserved because it actually meets back up there. Alright, so this one is also conserved. Now over to the electronic version. Alright, so we're actually going to check using our online vector sum if our diagrams were actually correct. So for the first one here, we actually had a magnitude of 27.4, so now we can actually use the extra decimal place as opposed to our diagram, and this actually dipped below the line at 12 degrees. If I go to the other vector, this was at 70 degrees. Oops, wrong one. So this was at 25.5 and it was at 70 degrees. So the vector sum is actually shown here in black and represented over here. So this is actually saying it's got a magnitude of 39.94. So I'm just going to round that up. So that's going to be 40 at an angle of 27.2 degrees. Alright. So that was the initial momentum. Now I'm going to plug in the final momentum. So the final momentum of A was actually 22.6, and it actually had an angle of 97 degrees, and the other one was B, which had a magnitude of 38, and that was below the line there at -6 degrees. So you can see here the magnitude is 39.6, which is almost the same as 40, and the angle is 27.7, which is also very close, given that the magnitudes were actually measured off a photocopy using a very imprecise ruler.